Okay, this week we're going to learn how to do semantics on sentences with quantifiers. So we have three new rules from F1. Well, three new rules that we didn't have in F1, but we have all the rules that we had from F1 still in our system. So, for example, we have the pass up rule still. So if we have something like A and big A, then whatever the meaning of little a is, and notice now instead of using a situation V, we have a model. So the set of situations in our world, and we have an assignment function. So that way we can deal with a binding and we can deal with pronouns. So we bring that up, and whatever the meaning of little a is, it passes up to big A. So we get MG there, and these have the same meanings. We also have a negation rule, a conjunction rule. Now our sentence breaks into a noun phrase and a verb phrase, but our sentence is still true if the noun phrase is an element of the verb phrase, if we have this exact pattern of an NP and a VP. And our rule for transitives is still the same, but keep in mind now we always have a model and an assignment function instead of some situation V. So that's an important difference. Let's talk about new rules that we have. The first rule is for pronouns and traces. So for pronouns and traces, we use an assignment function, but we don't evaluate anything until the very end. So for instance, if we have a noun phrase that has a trace in it, so NP to T1, then what this means, and let me just zoom in a little bit on this so we can see it more clearly. This just means that the meaning of the trace is the assignment function g on that trace. And later at the end of the derivation, if it's not bound, we would then check our list of things in our assignment function and we would see what T1 points to. So if we have a noun phrase going up to it, it gets the same meaning as its daughter T1. So this is also g of T1. We do not evaluate this until the end. If we have a pronoun, it works the same way. So if npro goes to she, usually what happens is we give this an index. So let's say this is she1. Then the meaning of she1 is just she1 in that assignment function g. And again, at the end of the derivation, if it's free, then we check our assignment function to see what it evaluates to. And of course, this would go up to a pronoun, which would have the same meaning as she, which is the same meaning as the daughter. So the assignment function on she. That's our first rule. So as another example, let's just do another example here. Let's say we have a pronoun to it, and this is say it too. Then to get its meaning, well, in a model and a function, we just use the assignment function on it too. So we don't know what that is yet, but we can check at the very end if it's not bound. And npro, mg, this is going to have the same meaning as it too in a model and assignment function, which is also going to be g of it too. Okay, so that's the trace and pronoun rule. Now we just have to deal with our two quantifiers, and then we're pretty much done with all the new rules that we have baked into our system as it is. So this current one is the rule for every b or every n. So here we're doing something a little bit different, and I should make this clear. If we have a quantified noun phrase, sorry, it shouldn't be an NC there. Let's say we have a word like every, make this a little bit more clear, every student. We do not give meanings now to every, the determiner, or the noun phrase. Instead, we treat this as a unit with the NC, the common noun, and we give an entire meaning to a sentence instead. So this is where we deviate a little bit from our rules before, where every node has to have a meaning. It does not happen with quantified NPs. It does not happen with determiners. It does not happen with the determiner word itself. Those will not have meanings, and we'll see that in a tree later. Instead, we have a rule for the sentence. So I will say that the student will have a meaning and the common noun will have a meaning, but we won't get another meaning until we get to this S level above, which connects to another S level below. So let's go over the rule. Let me zoom in a bit on it so we can read it. Okay. So now we're going to make use of assignment functions and binding. So let's say every student is indexed with a letter. Let's call this I. So this will be like a 1 or a 2 in our tree, or it could be an I or a J in our tree. We say that every B is S. So the example I give here is every student indexed with a 1, and then every student likes Kier, so T1 and every student are indexed. So let's say every student, that student likes Kier. This is true if for every D in our universe, so for all D in our universe, this means that whatever we have in our universe, we're going to pick a variable D, and it's going to go through everything. And if D is an element of B, and in this case, B here refers to our common noun. So if D is in that set, so every student, if D is in the set of students, then the sentence where D now replaces that trace is equal to 1. So basically we're saying every student D, if every D in the set of students, so if for every D in the set of students that we have, if D is in the set such that D likes Kier, for all of those Ds, then the sentence is true. So if every student likes Kier, then that means that every single student that there is must be in the set of things that like Kier. Okay, now I want to actually see this with an example because it's easier to understand the theory once we actually take a look at how this is applied. So our NP here is every student. So if I take a look at what this common noun will be, we would say this is the set of X such that X is a student in M. This M is our model. Okay, so let's say we have this, and then a determiner doesn't have any meaning we've associated with. So what we're said is that this one here, S1, basically says G of T1 likes Kier. So T1, the trace, likes Kier. So this is true if our trace is in the set of X, such that X likes Kier in M. And that assignment function is basically asking, well, what is T1? Well, now what we're doing is because we have every student binding it, G of T1 is now going to be bound in the next case. So now we say that the sentence with every n is true if for every D in our universe, if everything D in our universe, if D is a student, so if D is in the set of X, is that X is a student, then the sentence G of T1 likes Kier, so the set of X is that, or the set of GT1, or I should say, if GT1 is in the set of X, is that X likes Kier and M, is true. But GT1 is being bound. So actually, we're not thinking about whether G of T1 is in this set. We're asking ourselves, is D in that set for every single instance of D in our universe? So our requirement is asking, okay, this sentence is true if for every individual D in our universe, if D is a student, then D likes Kier. So I want to take a step back and I want to think about this in terms of predicate logic. Every student likes Kier. For all X, if X is a student, then X likes Kier. So this is our translation, right? Now what we're saying here is we're saying if, and I should put this out front, if for all D in our universe, so if for all D in our universe, if D is in the meaning of student, or D is in the semantic value of student, which happens to be a set, then D is in the set of X, such that X likes here in M. So I've sort of broken the predicate logic translation down into the components of meaning that we have in our rule. So hopefully if you see this, you can understand what the connection is here and why we have our assignment function. So the reason that we make this modification, D of T1, is so that way we're not looking at some particular individual that T1 eventually maps to. Instead, what we're doing is we're saying, okay, every student and T1, they're indexed with each other. They mean the same thing. But every student has to go through everything in the universe and look for particular things who are students. So what we're doing is we're saying, actually, let's make T1D. So that way, when we check everything in our universe, if it's a student, we also check to see if GT1 is D for that particular instance. So if D is in the set of X, just that X likes Kier. So there's a couple ways of thinking about this. One is just to look at the predicate logic translation. Another is to go through step by step with this meaning. But either way, you get the same result, and we'll see this in action a few times with actual trees. Now, the rule for the existential for some or is very similar. And again, this matches the predicate logic. So last time we did for every n, for everything in that noun. Now we're doing for something in that noun. So we say for some D in our universe, D is in B, so this is our common noun, and S is true where D is replacing that trace. So some student 1, T1 likes Kier. So let's take a look on the right side with the actual implementation of this. Again, we have NC, and this is just going to have the same meaning as student. So instead of X, we said X is a student. And then the determiner, which is, what is it? It's some. And the noun phrase will not have meanings, but the common noun and student will. Okay, so if the sentence is still T1 likes Kier, so the sentence is true if G of T1 is in the set of X such that X likes Kier and M, but as we go up to make this some student, it is going to be bound, which is what we see here in our assignment function replacement. So we say that the sentence is true if for some D in our universe, D is in the set of the students, and the sentence T1 likes Kier is true where D is now being pointed to from T1. So whatever element we're checking to be in the student, we also have to check to see if that element is in S1. And if that happens for at least one of those elements, then it's true. We just need to have some D in our universe where D is a student and D likes Kier. Now let's check why. Let's check our predicate logic translation again. This would be there exists an X such that student X and likes X Kier. So we just need to check for one of these. So basically we're saying there is some D in our universe where D is in students. Let me actually just write this out for real. I'll abbreviate a bit, but I'll write out the notation. And D is in the set of, well, S1 in this case, which is the set of X such that X likes Kier. So I'll just write this set up. So set of X such that X likes Kier. And we're using in a model M, so we write in M. But as you can see, once again, this does match our predicate logic translation. So D is in the student, and D is in the set of X such that X likes Kier and M. So that's it just for seeing how these rules work. In the next video will be a short one, but we'll run through this tree, which is one noun phrase. And then in the next video, we'll talk about trees with multiple noun phrases in them, so scope ambiguous sentences. Then we'll finish up with pronouns this week, and then that's pretty much everything. If there's any questions, as always, discussion board email. I'll get to you when I can.